hi. So today basically I'm going to go over Newton's second law and my interpretation of F equals ma. This closely resembles the impulse momentum theorem, and basically what I'm going to do today is basically say that if we have a force like my leg kicking a ball, so we can even draw it out. We have a leg and we have a ball and there's a small change of time, and if this leg exerts a force onto this ball, which was at rest at once, so we could even say our initial 0, and we have a small change of time, and this is going to be a force. We say that force multiplied by a small change of time equals mass times a change in velocity. So this change in velocity, if our initial was 0, then this one is basically going to say v final minus v initial, and our t is going to basically be our t final minus t initial. So t initial is going to be 0, t final there, and what we have is force times the small change of time equals mass times the small change in velocity. This kind of makes sense because if we apply force with a small change of time, the ball that was in rest now has a velocity. So it's kind of like a linear relationship almost. Then from here on, all we have to do to make F equals ma is, by knowing a little bit of calculus, if we bring the t over on this side, we essentially just get force equals mass times a small change in v over a small change of t. And small change in v, small change of t, could be represented as dv over dt, and we all know that dv over dt is acceleration. So we have F equals ma just from that example. Cool, right? Alright, now that we have F equals ma, we're going to concentrate on A. And then by concentrating on A, we could prove or derive these two equations real quick. So I'll keep this one up, but take this one out just because we have it there. And when we know that acceleration, I'll go on this side, when we know that acceleration is dv dt, all we're going to do from here is use a couple integrals and get this equation. So the first integral that we're going to do is to find our velocity. So by bringing the t over on this side, we have a dt equals dv. And also we just swap this around, which is the same thing as dv equals a dt, just to make things a little bit easier for our eyes. And then when we integrate this by doing from v initial to v final, and on this side t1 to t2, or t final is fine, we are basically going to get our equation of vf minus v1 equals a tf minus a t1. And we could factor out the a, and we could bring the v1 over on the other side, and we're going to get vf equals vi plus a, and tf minus t1 is change in t. So there we go, that's what we have. So that's kind of an extra equation that we just derived. Nonetheless, that's very important as well. And then I just put this one up because a lot of people kind of have, or they kind of wonder why this one is there. And this one is a little bit not clear as this example here. So there you go, if you got that on memo, I'm going to clear that off now. This one comes about because we looked at acceleration a little bit differently. So if we know that acceleration is dv over dt, this acceleration could also be represented as dv over dx. So velocities with respect to x multiplied by dx over dt. And notice if we were to, go back, all that would happen is that dx and dx would cancel, and we were left with the original equation. But in this time we want to keep the dx. And by keeping the dx, I'm going to rewrite that. And that's not a cross product, it's just multiplication. By having that, we know that this is v, and so we now have our new acceleration formula, which is, so dx over dt is v, and we have that it's v multiplied by dv over dx, and so keep this in your pocket as well, because this one is going to solve that one. Oh shoot, I erased the other one. I wanted to go on the first one, but I kind of sidetracked, but we'll go back onto the first one. So keep this one in mind, or should I just, I could just tell you guys which one this goes to right now. Nah, that's okay. I'll go with the first one. So keep that in mind. That'll come in handy. And so our first one, where we had Vf equals, I believe, V1 plus A changing t, right? So we kept that in mind. So now we also know that velocity is dx over dt. And by using this, we're going to go back, and we're going to go and say that dx dt equals v1 plus A, and we can just write that as t for now. Then when we integrate this, or by bringing the t over on this side, we'll write out all the steps. And then dt. So notice how the dt went on every single one. Then what we're going to do is we're going to integrate this. And we're going to have x1, our x final, so this is our position now, and dx equals integral. So now both functions are in terms of t, so we have t1 and t2. Then we have v1 dt plus a t dt, and simple integral is going to tell us that that's x2 minus x1 equals, that's going to be v1 t, and well, it could be changed in t. Well, you guys can understand that, right? Yep, change in t, and we'll just write that as t for now, just because most of the time t is 0, and we have plus acceleration, and then this one becomes the power of 2, and then divided by 2, so we have 1/2 a t squared. And all we have to do to finalize this is bring the x1 on this side, so we have our x final is going to be x1 plus v initial, or we could say v naught as our initial, times time, plus 1/2 a t squared. So that's our first example. Good, right? All right. And then going back to our acceleration, we're going to now solve and derive the second formula. And so with the second formula, we remembered that acceleration can also be represented as v dx dt. Oh, wait. Did I say that right? No. That's dv dx, right? Okay. I don't think I'm messing anything up, hopefully. And from here, we want to go and solve for v. So we essentially write acceleration. I'm going to keep this dv on this side. I'm going to bring the dx over on that side. So then we have acceleration dx. And then we want to create this function. So all we're going to do is integrate v dx equals, and bad. That's v. So this is going to be with respect, this integral is going to be with respect to a small change in velocity. So we could do v1 or v naught, as people say, v final equals, and then this one is respect to dx. So you have x naught, x final, and we basically have acceleration dx, and this becomes v final minus v naught equals, we have this, and acceleration multiplied by d final minus x naught. So this could be also represented as change of x, and I did that wrong. That's going to be v squared over 2, right? Because we already have a v, so v to the, we have to increase the power, then divide it by that power, so v squared, and this could be simplified as, I'm going to write it over here, 1/2 and v final squared minus v naught squared equals acceleration x minus xo. Then we bring 1/2 over on this side. Then we have v squared equals v naught squared equals 2x minus x naught. Then we bring, and then finally we bring the v naught over into the other side, and we have our final equation. Plus 2, oh, my a was gone. Silly me. Okay, x minus x naught. There we go. So we just derived f equals ma, sort of, and then from using acceleration, we could backstep, and we also, I gave you an extra derivation of v. Right, so v is v naught plus a acceleration times time. I gave you that one as well. And now I gave you v final squared equals v naught plus 2a multiplied by change in x. And finally, this one's a little bit, remember the acceleration one that I taught you a little bit earlier? This one can be used to figure out kinetic energy, which I don't want to go over today, but by using acceleration, I do want to show you guys why that works. So kinetic energy is directly in correlation with work, but just for now, remember that acceleration, I probably should have just left that on the board, dv over dx, dx over dt, and which is just v dx over dv over dx. So then when we write our formula f equals ma, instead of ma, we're going to write m times our acceleration represented in a different way, which is v dv over dx. And then from here, we're going to bring the dx over onto this side. So we are left with f dx. So this is what work is. Work is force times the distance, right? So we have work equals mass v dv. And then we're going to integrate both sides. So this one, we're going to go from x naught or x1, whatever you want to call, and x final dx equals mv. I'm going to integrate that, and then dv from v naught v final, and what we're going to get is we're going to get fx, f change of x, if you want to say, equals, and we have change of x because f is going to be from xf minus, or xf minus f x naught, so that's why it's represented as that. And over on this side we have, so v m, this goes up divided by that, and that's from that, so basically, finally, when we make it a little bit cleaner, we have our kinetic energy, or work, if you want to say, is 1/2 m, and it can be a change of, usually it's, we start from 0, so we could even just call it E squared. So that's where we get our kinetic energy formula, 1/2 mv squared. Sweet. I hope you guys enjoyed the video. That was just kind of my representation and my derivation of how I like to keep these formula in my mind. Hope you enjoyed, and hope you liked the video.